number 16 says, which of the following statements about the curve y equals x to the fourth minus 2x cubed is true? All of the answer choices have to do with the number of relative extrema and points of inflection. To answer this question, we need to understand what those are and how to find them. So let's start with relative extrema. Relative extrema is a catch-all term for both maxima and minima, and you can find maxima and minima on a function anywhere where you find the derivative changes sign. For example, a maximum point on the graph might look something like this. Notice how the graph changes from having a positive slope to a negative slope. So anywhere on the graph where we have a sign change of the slope or a sign change in the derivative, we will be able to identify a relative extrema. Points of inflection are found similarly. For points of inflection, we need to find the second derivative, and we are also looking for a sign change on that second derivative. Points of inflection are points on the graph where the concavity changes. To sum this up, relative extrema are points where the sign of the derivative changes, and points of inflection can be found anywhere the sign of the second derivative changes. So let's start with the first derivative. The function, and I'll just go ahead and rewrite it, y equals x to the fourth minus 2x cubed, can be differentiated using the power rule. Y prime will be 4x cubed minus 6x squared. We are looking for where the sign of this function changes. You can find sign changes either where the derivative equals 0 or undefined, but this function, this y prime, is a polynomial, so it'll never be undefined. So we really just need to find where it's equal to 0. To do that, we are going to factor out an x squared as a greatest common factor and set each of these two factors equal to 0 using the zero product property. We have a point x equals 0 and another point x equals 3/2 where we have a potential relative extreme. We do need a test to make sure that the sign is actually changing at these values. It is possible that the sign does not change when you find a critical value like this. To map this out, I'm going to just draw a number line for y prime. I'm going to plot the critical values, 0 and 3/2, and then consider whether or not y prime is positive or negative in between and outside of these values. So for example, if I substituted a number like -2 into y prime, and it might be easier to use the factored version, I will end up with a negative number. So between -infinity and 0, the function's negative. And when I say the function, I mean the derivative of y is negative. Between 0 and 3/2, I can pick a number like, say, 1, and if I substitute that into y prime, I'm going to get a negative number. So notice we do not have a sign change at x equals 0. What might be happening on the graph of y is we have a negative slope and then a negative slope after the slope becomes 0. So in that case, that would not be a relative extreme. Now, if I pick a number like, let's say 5, some number that's bigger than 3/2, and substitute that into y prime, I'm going to end up with a positive value. So notice here we do have a sign change at 3/2. Specifically, the sign is changing from negative to positive. So if on the graph of y, the slope changes from being negative to positive, it doesn't ask us what kind of extreme this is, but we definitely know that it is a relative minimum. Either way, there is only one relative extreme value. So we can eliminate some of these answer choices. A says there is no relative extremum. That's not right. D says there are two relative extremas, so it's not going to be D. And E has 3 relative extremas. That's not going to be the case also. So it's really just between B and C. And so we need to determine whether there is 1 point of inflection or 2. To find the number of points of inflection, we're going to do exactly the same thing that we just did, except with the second derivative. So we'll differentiate y prime and the derivative of y prime using the power rule once again. Y double prime is 12x squared minus 12x. To find those points of inflection, we're looking for a sign change on y double prime. So we need to find what I'll call the subcritical values of the function, which will be where the second derivative equals 0 or undefined. But just like with y prime, this is never going to be undefined because y double prime is a polynomial. So we're really just looking for where it equals 0. If I factor out an x from this expression, I'll have 12x minus 12, and that gives me a subcritical value at 0 and another subcritical value at 1. So just like I did with the previous one, I'm going to construct a little number line chart here with 0 and 1, and I'm going to test the values by plugging them into x for y double prime to see in these intervals whether the function is positive or negative. So if I plug in a negative value in here, for example, if I plug in -2, I will end up with a positive value for y double prime. If I substitute in a number like 0.5, I get a positive times a negative, which is negative. If I substitute in a number like 5, I'll get a positive times a positive, which is positive. So notice here how we have two sign changes. We have a sign change at 0 and a sign change at 1. Therefore, there are 2 points of inflection, and our answer is C.